Ah. All right. Okay. All right. Start. Okay. I'll wait for the students to come trickle in. I don't know what I'll do. I'll kind of talk about that example, that group from class, and then we'll collect some preliminary information about a finite simple group which has order 168. We'll see what the Silo theorems tell us. And then that's pretty much it. One day in this class, I'll prove for you that there's only one simple group of order 168, much like I did today for the number 60. So that's what these office hours will be. They'll be kind of mostly exploratory. Okay, so where to begin? Oh, hey Crow, what's going on? Welcome. Let's see. I want to talk about that weird group for a second that I introduced. Let's see. And students, you can go ahead and ask any, if you have questions about what happened in the material, go ahead and ask it on Discord under general. Ask it under general. All right, so what happened was I showed you a group during lecture. I showed you an interesting group. It was called GL3F2. All right, and it's a lot like It's a lot like GLN R, like GL3 of R. This is like 3x3 matrices. Invertible. But invertible had this other name, which was like determinant isn't 0. Okay, so you do the same kind of mathematics, also known as linear algebra. But now your number system is this interesting Z mod 2Z number system. This is just a fancy notation. Okay, why different notation? We're just chilling, so let me just start talking about this. You typically write F sub 2 when you're thinking about the same set as Z mod 2Z, but now you're also thinking about the structure of multiplication. Oh, thank you, Dank Rose. Okay, so in Z mod 2Z so far, or Z mod NZ so far, we've only been talking about the additive structure of remainders, if you notice, class. Hi, Auto Phoenix. So when I want to think about also the multiplication rule, like multiplying remainders from your 3613 class, modular arithmetic, but now the multiplication and addition structure, when I want to think about it in that bigger sense, I'll switch to the notation F sub 2. And that's typical in mathematics, all right? Okay, so F sub 2 is a number system. This is a number system. It's only got two, so to speak, numbers, two elements. You can add and multiply. You can add and multiply two elements, just like odd and even get multiplied. We're gonna learn all about this kind of situation in the latter part of the course, like probably starting in about a week. Rings and fields. That's the next topic. These kinds of gadgets. But what I want to just tell you is that this is now just matrices, invertible matrices, with entries in that new field. That's all it is. Okay? And the group law is matrix multiplication. Okay, so for example, how the heck do you find the inverse of an element? So for example, here's an element. Now you got to be careful. Just because you slap some ones and zeros in the matrix doesn't mean it's going to be invertible. You do have to check the determinant being non-zero, which just means 1. You have two options. Either it's going to come out to be 0 or 1. Okay, so for example, this is... yeah, this is determinant 1 matrix. But like, how do you find its inverse? Okay, there's like fancy ways using the cofactor matrix. You can do that in this case, but you just do your linear algebra row reduction garbage. I don't know if you remember this. You probably did this identity on the and then you do some garbage. Row reduction. row reduce, subtract and do this. Yeah. So, and then you see what happened on the right-hand side. I don't know if you all did this in your linear algebra type classes. However you figured out how to find the inverse of a 3x3 matrix, you do that, all right? And it'll work out. That's how, yeah, RDL, exactly, RDL. Wait, do you want, RDL, do you want me to do this one? Or anybody, do you want me to find the inverse of this using row reduction to see that it all works the same way? Whatever. Okay. Tell me if you do, and then I'll do this. But it's not like any different. All you're doing. It's tedious, kind of. Yeah, it's kind of tedious. It's not so bad. But yeah, all you have to do is, I mean, especially when you're working in F2. Remember, in F2, it's not bad at all. Because every time you add 1 plus 1, it's just 0. So like, beautiful. Okay. So you row reduce. That's how you find the inverse of an element. Okay. And so what I said last time is this group has 168 elements. That's how many invertible matrices in binary 0, 1 there are in the world. 3x3. Okay. So now what I'm going to do is I'm going to just keep talking about it, riffing on it. This group of matrices acts on vectors. Just like linear algebra worked for R3. Just like your R3 linear algebra. This group of matrices acts on, I'm just going to call it F2, 3. Just like R3, but now this thing, this number system, third, which you should just think of as column vectors. Okay, look. How does this matrix look, do the determinant, you'll get 1. I mean, it's the upper triangular, so the determinant's the product of the diagonals. All of linear algebra is just working. Okay, how does this act on 0, 1, 0? Oh, 0, 1, 1. Let's do an interesting vector. How does this is action. Well, it's this. By definition, you do matrix multiplication, just like always. You do this thing, so you're gonna get 0 times 1, 0 times 1, plus 1 times 1, plus 1 times 1. That's 1 plus 1, which is 0. Etc. What's the next one? Also 0. And then what's the last one? 1. There, that's the output. All right, good. Absolutely, RDL. Exactly. Everyone's on the same page. Please let me know, especially students, if you're not getting what I'm saying. I'm doing R3 linear algebra, but with way simpler. Just zeros and ones everywhere. Okay. Awesome. And so in this way, so this group of matrices acts on this thing. This thing is, by the way, called an F2 vector space. Okay? That's what we're doing linear algebra over the field with 2 elements. Field is a word that we're gonna learn next week, maybe at the end. F2 is an example of a field. So is R, so is C, so is Q, so is Z mod PZ for every prime. Okay, great. So matrices act on this vector space. All right, cool. Notice, the number of elements in this vector space, the total number of columns possible is 2 cubed, which is 8. All right. But there's always there's this one vector called 0 vector. There's this one vector, 0. There's a special one. Because when you act by any matrix, when you hit any matrix acting on the 0 vector, you'll get back the 0 vector. Quite clearly. You're always going to get 0, 0, 0 when you do this matrix multiplication action. Okay? This thing is an orbit. Okay? Huh. Oh, my hair went in my mouth. Okay. So that means that all the non-zero vectors So the matrices act on the set of non-zero vectors, which is a set of size 7. And in fact, it acts transitively. You might remember a theorem from linear algebra, which is like, you can cook up a matrix that sends 1, 0, 0, invertible matrix that sends 1, 0, 0 to any non-zero vector. You can always cook one up. You can just do it by hands here, folks, to find a matrix that sends 1, 0, 0 anywhere else. So it's fact that this action is transitive, you should try it. Oh, thank you. Oh, Crow is teacher's pet? Crow, teacher's pet. Awesome. Here, let me give you some positive feedback. Wow, wonderful. Okay, great. Awesome. So everyone understands that GL3F2 acts on some crazy set of 7 elements. Each element is like 1s or 0s, 3 of them. But you don't include 0, 0, 0. Okay? Remember that. Remember that. Okay, so now I'm going to just change subjects. Let's change subjects. I don't know if anybody here in this class has ever taken a geometry class. Have you all taken geometry? Proof-based class. CPCTC. Okay, Crow. Was it proof-based? Oh, thank you for the compliment. Yo. Sloth, you haven't? Okay, that's fine. That's fine if you... Many people have not. That's okay. Lowest math grade was in geometry. Okay. Well, no, was it proof based? I'm not talking about high school geometry. Maybe it was called axiomatic. Okay. So let me just give a crash course in. Let me just give you a description of what axiomatic geometry is like. Okay, so what axiomatic geometry is like? Okay, the goal of it is to make your Euclidean geometry that you learn about, like Pythagorean theorem and triangles and CP, CTC and side, angle, or whatever, to make that a rigorous mathematical subject from scratch. Okay? Riemann. Okay, whatever. Okay, so in geometry, there's a definition of what a geometry is. Okay, so there's the following notion. So what you define? You actually define geometry. And I don't want to go into the details too much, but here's the kind of thing that the definition looks like. Sloth. I'm talking to Sloth, basically, at this point. What you do is you sort of say this. A set is, let's call a geometry, if... so the points, the elements, are called points. And then what you do, Sloth, what you do is you define the notion of line. And at first you have like total freedom to declare what a line is, what lines are. Lines are just certain subsets. All right, so you have a set, which the elements, you just call them points. And then you have to define the concept of a line. And a line, at first, is just some subset of points. That's what a line is. But the lines have to obey some axioms. All right? The lines and the points have to obey some axioms. Axioms of creating a geometry on the set S. Just let's just think of it this way. I'll show you one of the axioms. You'll definitely agree with this axiom. Okay, one. Just gonna show you some. This is the main one. Two lines, two different lines, have to meet at a single point. Sorry, no. Meet at most one point. Meaning, a line is just a certain collection of dots, and another line is another collection. Two of them can only meet at most at one point. You're not allowed to have two lines that meet in 2 points, but are different subsets. They'll be the same subset then. Okay, so there's other ones like there's some interesting ones, like every line has to have at least 3 points. Wait, is that one? Is it 3 or 2? I forget the exact axiom. At least 2 or 3 points. Something like that. 3 maybe? I don't know. Whatever. Okay, etc. So let me just say etc. Okay? And what happens? Okay, great. I don't know them, Auto Phoenix. That's great. Awesome. Okay, so what happens, Sloth, is you see this first amazing example. One of the first examples you see of a geometry is called the Monoplane. All right? The Monoplane, Sloth, is a set that has 7 elements. There are 7 points. And I'm gonna draw a picture. It's just a graphical representation of this finite, an example of a finite geometry. Okay, so it's gonna have 7 points, and what you do is you arrange them in the following way, just because you can depict the situation easily this way. Okay, here's how you do it. You draw like an equilateral triangle. And you put this one dot in the center of mass, the centroid, whatever. So if you look at the total number of dots, there are 7 elements. It's just a set, Sloth. It's a set. And now I'm going to draw the, quote, lines. The lines are just certain subsets that have to obey some axioms. Like they can only meet at one point at most, and so on. And 2 points can only lie on one line. That's another one of the axioms. 2 points. 2 points can lie on only one line. Like exactly one line. 2 points lie on exactly one line. Some stuff like this, okay? All right. Let's do it. I'm now going to draw the lines, Sloth. I'm going to draw the lines. Okay. So, here we go. Okay. So you do this, and here they are. It's the magic. Here's one line. That's one line. Those 3 points. That's one line. Sloth. Okay. Here's another line. Those 3 points. That's a second line. Notice the 2 lines intersect at a single point. The bottom left corner. Okay, so keep going. This is another line. Sloth, I'm defining a geometry. Nobody says that this is true. It's not like a theorem. I'm constructing an example. It's called the Monoplane. So these 3 are lines. There are more lines. This is also a line. That's a line. Okay? I'll show you another line. This is a line. That's considered a line too. That triple of points. That's a line. Here's a line. That's a line too, the vertical one. And then there's one more line. Sloth, there's one more line. Because, Sloth, you see, if you look at this point and this point, right now, those 2 points don't lie on a line. They don't create a line. You see, there's no line that contains both of them. That violates one of the axioms of geometry, depending on how you start your definition. Okay? So, there's one more line that we put. And it looks weird, Sloth. Oh no, that looks really weird. See that circle, Sloth? It's not a circle, okay? There's nothing about circles or actual lines that you're thinking. It's just a subset. Those 3, they form a line. Okay? And if you take these 7 points plus these 1, 2, 3, 4, 5, 6, 7 lines, they form an example of a geometry. And it's called the Monoplane. All right, this thing's called the Monoplane. Monoplane. All right, it's a beautiful first example of a interesting finite geometry. All right, it's actually a very hard open problem in combinatorics to classify all of the possible finite geometries in the world. All right, Sloth? It's very hard. And this is the first interesting example that's not super silly. This one. Okay. Notice it has 7 elements. I'm now going to talk about a group. The Monoplane gives rise to a group. All right, there's a group lurking. Every time you see a geometry, you know, notion of lines, and I think it's technically called an incidence geometry. Okay, so I don't remember words well, I remember ideas. So I think what I'm talking about is something now called, I remember, incidence geometry. The axioms of incidence geometry. Monoplane satisfies it, and it's an interesting example. First kind of interesting example. Okay. So there's actually a group lurking here. I want to tell you what the group is, because the description of this group works for all kinds of incidence geometries. And it yields all kinds of interesting groups that you haven't seen yet, Sloth. Okay, so there's a group lurking here. It's called the automorphism group. Of the Monoplane. Let me tell you its definition. We'll call it F, automorphism. Let's give this the name script F, all right? Automorphism group of this Monoplane. Let me tell you what it is. You'll love it, Sloth. It's concrete. It's the set of permutations So this automorphism group, Sloth, is a subgroup of S7. The 7 is the set of dots. Permutations of the 7 points such that lines remain lines under the permutation. If I take 3 points that are in a line, I apply the permutation, those 3 points should also be in a line. Lines go to lines. That's the condition. So let me show you an example that would be bad, okay? Let me show you an example that would be bad. Here's a point A, and here's a point B. And here's a point C. If you take A and B and swap them, and swap C and something else. Okay, look. Do A and B and CD. This is an example of a and leave everything, all the other dots untouched. This is an example of a permutation that does not respect the lines. Because see, right. Because see, what it does is if you focus on this line L, L becomes the set A, B, D. You see, if I apply this permutation to the elements in the set L, the 3 points will become A and B, just swap places. So you'll still have A and B, but then C becomes D. So you get this. And A, B, and D don't form a line. Notice, look at that. There's no red line that goes through them. Does that make sense, Sloth? L doesn't remain a line under this permutation. Sloth, does that? Maybe Sloth isn't here. Okay. Okay. Whoever is listening. Oh yeah, Sloth, think about it. Look at this permutation. And apply it to the dots. Okay, apply it to the dots. Question: does the subset called L become another line? That's all I'm asking. Let's look at it. What happens to the 3 dots that are in this line called L? A goes to B. So you get B. B goes to A. Okay, you get these 2 output points. Where does C go? C becomes this point. So L, the subset L becomes this subset. Right, Sloth, exactly. But that subset is not a line. It's, so to speak, Sloth, these 3 points are not collinear, according to the definition of the Monoplane. Because look, A, B, and D, none of the red dotted things go through A, B, and D. None of the, there's like, you see, none of the red lines go through A, B, and D. Does that make sense? This set is not one of the lines. Yeah? So straight lines didn't get sent to lines under this permutation. So what's the automorphism group? It's those permutations of the 7 points which send a line to a line. What is this? What the heck is happening here? What is this? Who is this? Oh, hey, teaching stream. Awesome. I'm all for teaching streams. Oh, it's different language, it seems. Is this a different language? Who is your leader? Who is your leader? Identify your leader. Fred. You know what, Fred? I always enjoyed your streams. You're one of my favorite streamers, Fred. I think you're great. How do you spell your name? Okay. Fred, everyone, go check out Fred. Incredible streamer. One of the best. It goes Fred, then XQC, then me. That's the lineup of Twitch streamers. Everyone go check. I've been watching Fred for ages. I totally know what they do, and it's, let me tell you, it's something else. It's something else. What does he do? BPS, what does he do? BPS, what does Fred do? Physics. Yeah, physics. You know, he's one of the top 10 physics streamers in science and tech. Incredible. Incredible, Fred. That's really cool. Thanks, Fred. Yeah. You too. You're doing so great. I think. Yeah. Awesome. Awesome. Okay, let's go back, Sloth. Me and you, Sloth. Okay, I'm talking to Sloth and my other students. So, whenever you see a geometric situation, Sloth, some dots, and then they're constrained by some strings, like this Fauna plane. Or you can think of this as kind of like a graph. I don't know if you know graph theory or anything like that. It's some dots, and certain of the dots are called collinear, and some of them, etc. When you have a geometric setting, an automorphism group arises. It's the group of symmetries of this situation. The group of symmetries of the Monoplane. That's how you should think about it. Okay, awesome. It's the permutations that preserve the structure of line, lineness, collinearity. Okay, now here's the thing I wanted to tell you about during this office hours. Very chill, simple office hours. All right, here's the amazing thing. You haven't seen it before. Remember that first group I told you about? Linear algebra over 0 and 1. Only zeros and ones. 3 by 3 matrix. Okay. This is isomorphic to the automorphism group of the Monoplane. Why? Why is that true? Sloth, I can hear you asking. Why? Why should this be true? Okay, I'm gonna draw the Monoplane again. Let's practice this, Sloth. Me and you. Let's do it. Boom. Equilateral triangle, Sloth. You draw it and I draw it. Hopefully yours looks better than mine. Draw the lines, Sloth. Draw all the lines. Line number 1, or whatever. Here's a line. These 3 points are in a line. These 3 points are in a line. These 3 points are in a line. And then the funny line. Okay. Now next to each dot, Sloth, I'm gonna give these dots very, very strange looking names. Okay, Sloth? I'm gonna give these dots really weird names. Let's call this dot 100. That's what that one's called. Can you see that, Sloth? 100. Just for fun. Just do this, okay? Let's call this 010. And let's call that one, I don't know, 001? This Sloth, this office hours has no point. I'm just playing. I'm simply playing around, showing you some weird conspiracies. This is a QAnon conspiracy office hours. That's all. That's all I'm doing. Don't expect some grand thing. Okay. There you go. Just label those three like that. And then, Sloth, I want you to label the other ones like this. Now be careful. I gotta concentrate. Yeah. Sloth. This is time for Shungite, okay? We need Shungite now. We're told. In fact, if you look at this, you look here. There's a Fauna plane right here. Okay. Sloth, I gotta concentrate here. This is hard for me. This is hard. Hey, Sloth. Sloth, what is the center dot going to be called? What is the center dot going to be labeled? Can you guess? Yeah, the I. The I in the 111. Good. Yeah. 111, Sloth. Good. 111. Hey, Sloth. Have you ever seen one of those like magic squares where like, oh, all the rows add up to something and all the columns? It's on the back of the cereal box. You might see these. Yeah? Okay. There is a Shungite conspiracy here. Anybody see the pattern in this labeling? Notice. If I take 2 dots and I add the vectors, if I take 2 dots, 2 of them, and I add the vectors, or if you take all 3 on a given line, they all add up to 0, 0, 0. You see that? Do it, Sloth. Add up all the. And by the way, Sloth. If you add up 3 that are not on a line, they will not give 0, 0, 0. Sloth, this is getting deep. This is really cool. This is getting deep, okay? We're going really deep. I'm not done. Let's keep going, Sloth. Let's keep going. Ready? Let's keep going. Here's an interesting thing I wanted to show you. Suppose here's a riddle for Sloth. Suppose I took an automorphism. And all I know is where sigma sends 1, 0, 0, 0, 1, 0, and 0, 0, 1. Pretend somebody said, hey, Sloth, I have a automorphism of this plane I don't know the full description. All I know is where the blue dots end up in the permutation. I only know where the 3 blue dots, the first one, the second one, and third. That's all I know. Here's something cool. Here's a riddle. Then, sigma is uniquely determined. In other words, if you want to know an element of the automorphism group of the Fauna plane, it's enough to know what it does to those 3 elements, to the 3 blue elements. Why? Why? Let's think about it, Sloth. Let's think about it. Pretend you knew where 100 and 001 went. Right? Pretend you know where these go. Oh, they went to some 2 dots somewhere. Okay? I don't know where they went. We're pretending we know. Okay. Those 2 dots, they lie on a unique line. Notice that. Just you look at the Fauna plane, take any 2 dots. They will lie on a unique line. And so, the 3rd dot here, it has to go to that 3rd dot in the other line. Once you know where 2 of the points go, the 3rd point in its line has to go to the 3rd point in the output span. See what I'm saying? If you know where the 2 points go, the 3rd one has to go to the line's 3rd point. So if you know where those 2 go, this one's output is determined. Okay? But then we're pretending we know where all 3 of these blue dots go. So this one's output is also determined, and this one's output is also determined. But then hold on. You know where this one goes, and you know where this one goes. So this one's output is also determined. In other words, all you need to know about an automorphism is where it sends 100, 001, and 010. Okay? That's all. That's my observation for you. Okay, that's my observation. Once you know where what happens to those 3 dots, everything else is frozen into place, determined. You might have heard this kind of a statement. I don't know if you've seen this, or anybody in the chat, but this kind of thing rings a bell. It's a lot like that linear algebra fact. If you know what a matrix does on a basis, you know what the matrix does on everything. It's it definitely rhymes with that. So now what I'm going to do, I'm going to construct a homomorphism. So there is a homomorphism. Magic. M. Here's the homomorphism. Sloth. You send a matrix. Oh crap. Matrix A. Matrix A, 3 by 3, bunch of ones and zeros, invertible. Matrix A gets sent. The effect that A has on the 7 points. Just apply the matrix to these dots. You'll get some permutation of those 7 dots. But you have to ask, Sloth, why is that permutation in this automorphism group? You have to check. Sloth. Fun riddle. Check that A actually gives, actually respects lines. And the reason why A respects lines is that matrix multiplication is a linear transformation. That's what makes the fact that a line, that's what makes the lines go to other lines. Okay, so any matrix with ones and zeros, 3 by 3, invertible, produces an automorphism of this Monoplane. And so now what you check? M is injective. Now to check M is injective, you can use this riddle. If you have a matrix that does identity, well, it has to send this. Well, it's kind of obvious. It sends this to itself, it sends this to itself, and it sends this to itself. So it's the identity matrix. That was okay. That's easy. Yeah, that's easy. Okay. So then you check surjective with the riddle. And I think this is where the riddle comes in. You can obtain any permutation in the automorphism group of the plane by a matrix. Right. Okay? So that's the that's how you show that GL3F2 is some other thing. It's the symmetries of the Fauna plane. Okay, why do I bring this up? Why bring this up? I'll answer that now. One day, I'll show you. One day, once we practice silo theory and counting arguments, like you're gonna practice in your next homework assignment, in this current homework assignment, one day I'll show you one day I'm going to show you this. And you have to ask, how on earth are you going to show this? How on earth will you do this? The answer, the method It's going to be a crazy... This one is crazy. Way harder than 60. The method will be to prove that this group is isomorphic to the symmetries of the Fauna plane. Where will the Fauna plane emerge? Sloth, let me show you why this is a plausible method. The Fauna plane automorphism group is ultimately a combinatorial thing. You see, the proof is going to go like this. Hey, you know what? We have this group G. Let's look at some of its Silo subgroups. Let's study them. From the group, from the internal anatomy of the group, I'm going to find 7 things that the group is going to act on. And then we'll notice that the group acts in a funny way. Like, some of these 7 things, 3 at a time, form certain kinds of distinguished subsets. Distinguished triples of these 7. These 7 have certain structure. Like, there's a notion of 3 of them being distinguished, or let's call it collinear. And the way the group acts is it'll respect collinearity. And if you write out the incidence structure of the 7 things and what collinear means, it will look exactly like the Fauna plane. So that's the strategy. The strategy is to produce within the group 7 things. The 7 things get clustered into 3s. And if you map out how the clustering looks, it looks exactly like the lines in the Fauna plane. And the group will act on that via conjugation, exactly like the automorphism group of the Fauna plane acts on the Fauna plane. So that's how the strategy goes. It's beautiful. It's absolutely stunning method, but this is how you prove that there's only one group of size 168. You get yourself to the Fauna plane somehow or another. So that's what we're gonna do one day. Maybe an office hours sequence. Maybe even move it to next semester if we have to. But that's what I want to sort of build fluency towards. Showing you that there's also only one simple group of order 168. And it's this one, which is also GL3F2. Great. That's what I want to build up towards. For now, just play around with the Fauna plane and play around with this automorphism group AUT-F. See if you can understand it spiritually, or maybe try to prove this isomorphism. GL3 to the automorphism group. See if you can prove it. Okay. Great. All right, so now that's enough of my scheduled content. Oh, second EAG. What book do we use? We're using a book called Gallien's Contemporary Algebra. But to be honest, a lot of the theory comes straight from me. Okay, obviously I learned it from somewhere. Many sources. But the book is really heavy on like examples, like concrete situations and examples, which makes it great. It has tons of exercises, wonderful. But there are some ways of going about it that I find unnecessarily elementary. Like, I've just been using homomorphisms and the concept of group action, I set it up just super general, way more robust and flexible. Galleon does this weird thing where he only acts by groups that are subgroups of symmetric groups. It's weird, okay? So I'm using this, but next semester we'll be using next semester is Galois theory, and we'll be using a fun book. It's Stewart. This is kind of a modern classic for Galois theory. So yeah, that's gonna be a really fun class. Okay, see you, Sloth. Bye. I do teach online. What do you... What... What? Hey, Gath, how's it going? Gath is in the house. Everyone, stand up. Everyone, stand up. Gath has entered. We salute you. And you're... Gath is basically writing a textbook, like live. You can see it. It's like amazing notes on difficult topic, organic chemistry. You can see basically a textbook emerging. Wonderful. I should have been doing that, but I'm lazy. So that's one of the problems with that approach. Yeah. Oh, they're pretty good. They're pretty good. I mean, they're way better than... Vixen, I don't know why you want to be enrolled. It's just... You just get credit. You can still try to hang with the class and understand the lectures. Benzodephenanthrene. Yeah, Rex. Yeah. It's algebra. Rex, this is an algebra class. It's just it's called algebra. It's actually called Algebra 1. No. Aethual, I got this. Gath, I'll explain. Okay. Okay. Look. So it's not that you draw these kinds of things.
Yes, science! Yes, science!
Fisher projections. Yeah, Fisher projections. Right, sure. For sure, yeah. Right. Yeah, I agree with you, Vixen. Yeah, Pyrene and Sigma Aldrich, they're typically, you know, they're different schools of thought on this, really, and The real difference is the
science.
chirality, I've found. I mean,
Yes,
in my
science.
opinion. Wait, this molecule's weird? Wait, what's wrong? Wait, what's wrong with it? Oh, I'm supposed to do this. Is it better? This is looking more like it. Good. You know what that means, folks. That's funny. That's funny. No, I am. Look, I just drew a molecule. I definitely know. I've been learning this from Gath. This is what Gath has taught me. That's how good she is as a teacher, folks. All right. Time for credits, right? Credit time. Who is teacher's pet? Tropical. Oh, someone wants a twisted cubic? 30 minutes ago, someone ordered a twisted cubic, and they never came back. All right, here, Dank. Here's your twisted cubic. You see it in the middle there? There it is. Twisted cubic. The first example in algebraic geometry. Speaking of algebraic geometry, on Thursdays, is your class really easy to see online? Yeah, it's on my channel. You're looking at it. Like, look forward. Look into your screen. Like, kind of in the middle. Yeah, but in the mornings I teach, Vixen. Maybe you're not awake. I teach in the mornings. Look at the VODs or whatever, Vixen. Click on VOD, wherever that is. Okay. And then I have a YouTube where I try to put the VODs regularly. I save them on YouTube, Vixen. I don't know which one where I stopped. Okay, but you know, Vixen, you're asking the good questions. So, you know, okay, actually, hold on. Tropical Geek comes first, of course. Teacher's pet. Gath is here. Every time Gath is around, it's just, you know, everything lights up. Gath is cool. BPS is cool. I don't know who else was here that's a mod. Was Smash Time here? Was Algebraically Challenged here? Oh wait, who this? Fred. Fred. You know what, Fred? Fred. Just awesome. Overall. Awesome fellow. Go watch his stuff. I just love it. I just have it on all the time. Just lurk, you know? Just lurk in Fred's place. Okay, then who else was there? Sloth. Sloth. VIP. It's always good to have a student that you're talking to directly. And in the online environment, that is hard. So Sloth, that's my target student right there. Time to go play tech. What's technique? What is that? Some kind of math nerd, you know, math club activity? What is that? That's just hilarious. That's just so hilarious. Okay, there's RDL. An AI, I think I saw AI in there at some point. These are my real students. Who else? Who else gets it? Crow. Crow sneaks up here because of corruption. Scandal. Crow goes to the top. Awesome. Amazing, Crow. Crow funds this whole thing. Yeah. Wait. Scandal like that? Okay. No links. No links. No links. You know why? You know why? Because you all are gonna rickroll me one day. Exactly. BPS had one meal because of Crow. Thank you, Crow. You gave BPS his one meal of the month. Awesome. Okay, Vixen. Who is Vixen? Vixen's a new friend. Don't know who they are. Vixen. New friend. Who else is out here? Who else was in here? Who is Avual? Avual? Who is that? New friend. Rex. Rex. New friend. Who else do I see in here? Second EAG was here. That's an old friend. Stop coming. So actually just remove that. Okay. Who else is here? Fred was here. The Portuguese stuff in the chat. Incredible. Dank. Biotech Nick. Very nice. I am a fan of this plane. I am sorry, Biotech Nick. I didn't read that funny joke 3 hours ago. That was a funny joke you made, if you're out there. Good job. Okay. Oh, he's here. Biotech is here. Biotech. Funny guy. I'm a fan. This guy. Get it? Get it? I made that joke up. I made that up. Alright. I already told you some fancy things to say, Crow. Tayo just does a really good job of not reacting. Yeah, but he's good at it. He filters it. He's like a master. He's very used to it, I guess, at this point. Wow, fighting words by Tropical Geek. Lack of loyalty. Accusing Crow of lack of loyalty. All right, let's go back to the credits. Oh, this molecule makes it too. All right. Okay, folks. Today I taught you, not really. I just explored the Monoplane. And the final plane will be the center, the centroid of a vast conspiracy. It will turn out that any simple group of order 168 in this world will have to be isomorphic to the symmetries of the Fauna plane. Let's put the Fauna plane in here. One last time. We'll see it again one day. One last time. Everyone draw it with me. Final plane. It will show up by magic in the proof of uniqueness of simple groups of order 168. Beautiful. Let's go. Credits. Crow. For the cash. Transaction. Oh, thank you, Ivan. Thank you, Reed. Thank you, Why Problem. Thank you, Price of Freedom. You guys didn't make it in the credits, though. Somehow. Fred. Tropical. Tropical is teacher's pet. Fred. You know, networking. Good, career reasons. Sloth. RDL. AI. Good students. I mean, all my students are good, but especially great. Vixen. Ethual. Rex. New friends. Biotechnic. Stand-up comedian. This is benzodiazepine. Is that right? And then the final plane. Okay. Free Shungite today.
Yes, science! Yes, science!
What is he doing?
He's beginning to believe.